And today we would like to present our senior design project, which is an apparatus for remote control of humanoid robots, or ARCHR for short. Our overarching goal is to intuitively control humanoid robots remotely. So in 2011 in Japan, following a major earthquake, a tsunami disabled power supply and cooling of 3 Fukushima Daiichi reactors. Due to radioactive contamination, personnel were not able to enter the site to perform crucial tasks that would contain the meltdown. Robots did come to aid, but Japan was unsuccessful at utilizing them in the disaster area. In the direct response to the Fukushima Daiichi disaster, DARPA started the DARPA Robotics Challenge with the goal of developing ground robots capable of executing complex tasks in dangerous, degraded, human-engineered environments. What they were looking for is 7 capabilities, 2 of which are situational awareness and dexterity. Various humanoid robots participated in the first stage of the challenge and met these, but we noticed that it was difficult for the human to control these robots. This in turn inspired us to work on designing a controller that was easy to use and intuitive, while also providing the user with sensory information, so that it could be quickly deployed and easily operated in the disaster area.
Our system is comprised of 2 distinct components that work together either over a network or fully remotely. The first is a scaled physical controller of the robot that we call kinematically scaled. So if the user moves the controller's arm forward, the robot's same arm will move forward in the same manner. This allows for any robot to have a kinematically scaled controller, and regardless of the robot's size, big or small, and it will allow us to be able to easily control it. We've also implemented haptic feedback so that if the robot encounters resistance, the user will be able to feel that and understand the constraints. The second component is a stereo vision and virtual reality system. The video feed from the 2 cameras are overlapped in front of the user to give them a feeling of depth instead of using complex visual processing. And then the virtual reality system tracks the user's head movement so that if they look left, right, up, or down, the robot will look in the same direction. This fully immerses the user into the robot's area of operation and makes it feel like they are performing the tasks themselves. This meets our ultimate goal of being able to have a specialist in a needed field, rather than a specialist in robotics, be able to perform complex and technical duties.
So to test our design, we held 3 demonstrations over the course of 4 days to showcase our project and to get user feedback regarding our system and their experience with it. Users range from elementary school students, middle school students, college students with various majors, and even faculty members. So what we found from these tests is that our system is unique among other controllers currently in use, because even first-time users were able to intuitively and easily complete tasks in a short amount of time. So one would expect hours of on-site training or a need for certification to be authorized to control a humanoid robot, but here we are demonstrating that virtually anyone could have a full control over a robot upon first being exposed to it.
After the testing, we polled various users to see where they thought that our system would be able to be used, and the results are displayed above. So we decided to have a full-scale test of the robots, having 2 robots perform a cooperative task. As you can see on screen, the large robot is using his height in order to pick up a specimen that could be dangerous to a human. He's being controlled by a member that's there, but they could also teleoperate it. The specimen is then handed down to our custom robot, which utilizes its mobility in order to transport that specimen outside without the need of a person being there. These robots can be deployed in a variety of areas without having to be reprogrammed in order to operate in their environments, in their new environments. So they could be deployed to West Africa and be controlled by medical experts in order to not expose them to Ebola. In fact, the National Science Foundation has put out a broad call for ways to stop the spread of Ebola, and a version of our ARCHR system is going to be submitted as a method of doing just that. So we are greatly looking forward to the continuing possibilities of the uses for our system, and we will also have a display outside. Thank you so much.
I know you people designed it because the robots earlier did not do as much the humans wanted it to do. So you actually programmed it to do just the way the humans behave. So there are a couple of questions with regard to that. What if the robot falls? How will you make it get up? I mean, I see the tall robot, and if it's going into, I mean, there are certain conditions you have programmed in terms of moving the arm and all, but if it falls, have you thought of that?
We have not gotten to the point where if it was falling down, how would we get up? We would probably try and implement some type of a protocol in order for it to get up, because we know that various like toy robots will fall down. They have a protocol where they know how to manipulate their appendages in order to stand up. So that's something that could just be a program call that we would be able to do.
Sure, and then the second question is from a robotics perspective, what is the remote distance you can control the robot from?
Well, it works over a network right now. So if we had network access from one computer to the next, it would be able to work pretty much at great distances. So they could be in different buildings, they could even be in different cities, as long as they had a good secure connection for the transfer for the information.
So how far have you tested?
We've tested from the length of a hallway, basically. So we have one computer with the control system, and then we have an onboard computer for the mobile robot, and it's able to maneuver around away from the area. Right now, about the length of a hallway.
Thank you.
From DARPA, the greatest challenge that we're having right now is actually having the humans communicate with the robots, because, you know, as emergent disaster sites, they're not going to have great Wi-Fi.
Yes.
So that's just something to consider for that.
Yeah, we are working on implementing bandwidth as well as latency restrictions in order to see how low or degraded the situation can be for it to operate effectively.
Thank you.
Well, you know, coming from the network side of things, I was going to ask that, but obviously, if you keep the bandwidth low, you could even have a satellite communication to dictate that. The other comment that I had that I thought was really intriguing about this is that if you can take something really as technical as robotics and you bring a human element into it, which I really like what you guys did, right? You said, I can have a doctor operate this, I can have somebody in that field operate that. That was just a comment I had, that we all as engineers like to make things really hard and difficult. And if you can make it simple, even though it is difficult under the hood, it just has a long way to get us. I agree with you guys on that.